going to go through the second part in our two-part series on limits of matrices. To begin, let's review some concepts of complex numbers and p-norms. Remember that we really have the following two motivating questions. Let's say that we have an n by n matrix. We know that to find the exact eigenvalues of the eigenvalues lambda, we must compute the roots of a degree n polynomial. But instead, is there a way that we can find an approximate set of values for these lambdas? And must these roots lambdas always be real numbers? We can see that with the matrix on the lower left-hand side, that the entries of the matrix are integers, and therefore the eigenvalues are integers. However, with the matrix on the right-hand side, these numbers are not quite integers, but it appears that the numbers away from the main diagonal, namely 3, 5, 7, and 9, are very close to being 0. So we expect the eigenvalues, lambda 1, 2, 3, and 4, to be approximate to the eigenvalues that we found before. Let's recall a definition. We'll say that I, namely the square root of minus 1, is the root of the polynomial f of x, which is t squared plus 1. We'll denote a complex number z as a number in the form a plus bi, where a and b are real numbers. And we'll denote bold letter c as the collection of all complex numbers. Recall that c, under addition and multiplication, is a field. We also have the fundamental theorem of algebra that says every polynomial with coefficients in the complex numbers has at least one root in the complex numbers. To this end, let's say that A is any n by n matrix with coefficients in C. Then its characteristic polynomial always has roots in the complex numbers C. We'll give another set of definitions here. Following the appendix, that is what we just worked out, the absolute value or modulus of a complex number a plus bi is the real number square root of a squared plus b squared. Now we'll define the p-norm of a vector. Fix an extended real number p, that is a number p between 1 and infinity, where p could be 1 and p could be infinity. For any n-dimensional vector x, let's define the p-norm as the following real number. Either it will be the sum of the pth powers of the absolute values of the coordinates x sub j of our vector, and then we'll take the pth root of that corresponding number whenever p is greater than or equal to 1, or we'll choose it to be the max of the absolute values of the coordinates whenever p is infinity. We'll also define the p-norm of an m by n matrix A. Let's consider the following two vectors, a times x, which is an m-dimensional vector, and we'll compute the p-norm of that. We also have x itself, which is an n-dimensional vector, and we'll compute the p-norm of that. For any non-zero vector x, let's take a look at the ratios p-norm of a times x divided by the p-norm of x. The largest of these values is what we define as the p-norm of a matrix A. Unfortunately, it's very difficult to compute with this in practice, but we'll see some properties of this p-norm of a matrix throughout today's lesson. For example, let's say that A and B are two m by n matrices, and let's let C be a complex number. Then the p-norm of a matrix satisfies the following properties. First, we have positivity. That means that the p-norm of an m by n matrix A is always greater than or equal to 0. Next, we have non-degeneracy. That is, the p-norm of a matrix is 0 if and only if A is the m by n 0 matrix. Next, we have multiplicativity. That is, the p-norm of a scalar, C times a matrix A, is equal to the absolute value of the scalar C times the p-norm of the matrix A. Next, we have Minkowski's inequality. This says that the p-norm of the sum of two matrices is less than or equal to the sum of the p-norms. We have the following two values. First, let's denote rho sub I as the sum over the absolute values of the entry in row I. Next, we'll denote rho of A as the maximum of each of these rho sub i's. This is equal to the infinity norm of our matrix A. Similarly, let's let nu sub j be the sum over the absolute values in column j. And we'll denote nu of a as the max of these nu sub j's. Then this is equal to the 1 norm of our matrix A. If lambda is any eigenvalue of A, then the absolute value of the eigenvalue is at most the p-norm of a matrix. In particular, the absolute value of any eigenvalue is less than or equal to the smaller of the row of A and nu of A. Let's say that A is any n by n square matrix. Recall that the eigenvalue lambda must be a root of the characteristic polynomial. We can actually use the above to find an algorithm to compute the approximate value of these roots lambda. Again, let's let row of A denote the sum over the absolute value of the entries in row I. We'll also denote AII as the entry along the ith diagonal, the entry in the ith entry along the diagonal of our matrix A. We'll denote C of I as that disk that consists of those complex numbers such that, in absolute value, z minus AII is less than or equal to rho I minus the absolute value of AII. This is actually a disk of radius rho I minus AII centered around this entry AII. The theorem, namely Gershgorin's disk theorem, says that each eigenvalue lambda of A must lie in one of these disks, Ci. The Ci's are sometimes called Gershgorin disks. And notice that if 0 is not in any of these disks, then this gives us a quick way of determining when a matrix A is invertible. We'll use all of this today to talk a little bit more about properties of an infinite sequence of matrices. But first, let's talk about limits of sequences of complex numbers. Let's consider a sequence of complex numbers z sub k. We'll write this expression, the limit as k increases without bound of z sub k equals z sub infinity, for some complex number z sub infinity, really means given a real number epsilon that is positive, we can find a real number delta that is also positive, such that in absolute value z sub k minus z sub infinity is less than epsilon whenever k is greater than delta. Similarly, the expression the limit as k increases without bound of z sub k equals infinity means given a real number epsilon that's positive, we can find a real number delta that's also positive such that in absolute value z sub k is greater than epsilon whenever k is greater than delta. We'll also say that this sequence, quote, increases without bound, unquote. Here's a graphic to explain what's really happening here. The blue dots, red dots, and green dots would all be complex numbers. You'll notice that for the green dots, we have a disk. This disk would consist of all of the elements that look like they're centered around the point z sub infinity, and the disk has a certain radius. We can call this radius epsilon. The idea here is that we can move far enough out in the sequence, that is, we have the red dots, which then turn to green dots, such that if we move far enough out in the sequence, that is, if k is greater than delta, then everything should sit inside of the disk. That is, in absolute value, z sub k minus z sub infinity should be less than epsilon. There's also another mathematical way that we can make sense of the statement, the limit as k increases without bound of z sub k equals infinity. The idea is to consider instead of the complex numbers as numbers, we'll think of them as points on a sphere. So if we have a complex number a plus bi, we can now write that as a point on the sphere as the point p, which is UVW. In this way, we'll identify the north pole of the sphere, namely the point 0, 0, 1, with infinity as a, quote, complex number, unquote. This means that a sequence of complex numbers z sub k actually corresponds to a sequence of points p sub k on the sphere. So now let's try to make sense of the expression the limit as k increases without bound of p sub k is some point p sub infinity. This really means given a real number epsilon that's positive, we can find a real number delta also positive such that the 2 norm p sub k minus p sub infinity is less than epsilon. Here you can see a formula that actually goes as follows. If z sub k minus z sub infinity is small, then the 2 norm between p sub k and p sub infinity should also be small. However, if z sub infinity itself is infinity, then one would have to reinterpret this formula here to simply mean that we're trying to have our p sub k's to get closer and closer to the north pole 0, 0, 1. That means the statement, the limit as k increases without bound of z sub k equals infinity, really can be interpreted as saying the limit as k increases without bound of the point p sub k should be the north pole 0, 0, 1. Let's give an example of this definition. Fix a complex number lambda. Let's now consider the sequence of complex numbers z sub k equals lambda to the k, for k being 1, 2, 3, and so forth. We claim that the limit as k increases without bound of z sub k is either 0 if the absolute value of our complex number lambda is less than 1, it is equal to 1 if lambda itself equals 1, and it'll be infinity if the absolute value of our complex number lambda is greater than 1. Let's return to the graphic that we had before. Here you can see what is happening is the red dots seem that they are spiraling in towards the green dots, which are spiraling in towards the point. This is exactly what's happening here. That our lambda, as we raise it to powers, we see that we find a set of complex numbers z sub k that seem to be spiraling in either towards 0 or 1, and in some cases they just may spiral away and go all the way to infinity. Here's a proof of this proposition. First, let's write lambda as a real number times e to the I theta using Euler's formula. If you haven't seen this before, don't worry about it. We can write lambda as a plus bi, and let's write r as its absolute value, namely the square root of a squared plus b squared, and now we have an angle theta defined in this way. Cosine theta we'll write as a over r, and sine theta we'll write as b over r. It may be helpful to think of a right triangle where we have two legs of lengths a and b, and the hypotenuse here has length r. Again, observe that r is the absolute value of our complex number lambda. In order to prove the theorem, we're going to consider 3 cases. First, let's say that the absolute value of our complex number lambda is less than 1. Well, here, if an epsilon positive is given, we can choose a positive delta as you see on your screen. This is a matter of making sure that whenever k is greater than delta, then the absolute value of z sub k minus 0 is less than epsilon. Hence, from the way we set up our definitions, the limit of the z sub k actually tends to 0. Next, let's say that lambda is equal to 1. In this case, then every z sub k equals 1, so the absolute value of z sub k minus 1 should be equal to 0. But this is less than epsilon for any positive epsilon. So again, by definition, we see that z sub k has to tend to 1. Now let's take a look at the last case when the absolute value of our complex number lambda is greater than 1. Again, given a positive real number epsilon, we can choose the positive delta in a clever way such that the absolute value of z sub k is greater than epsilon. In this case, from the way we set up our definitions, the z sub k's should increase without bound. Now let's use all of this to define a limit of a sequence of matrices. We've tried to introduce p-norms to explain that there are many, many ways to define when two matrices are close to each other. Now we're going to prove that all of these definitions are one and the same. Let's say that we have a sequence of m by n matrices A sub k. The following three statements are equivalent for any m by n matrix L. First, for each extended real number p, we can find the delta such that given a positive epsilon, the p norm of a sub k minus L is less than epsilon whenever k is greater than delta. Again, this should be true for each and every given extended number p. Second, let's say that for some extended number p0, we can find a positive delta such that for any positive epsilon, the p0 norm of a sub k minus L is less than epsilon whenever k is greater than delta. Again, this says that this should hold for some extended number p0. And finally, we have the following m times n limits. That is, let's take a look at the ij entry of the matrix A sub k. And let's take a look at the ij entry of the matrix L. These are now just complex numbers, and actually the ij entry of the matrix A sub k generates a sequence of complex numbers. So now we can make sense of the following statement. The limit as k increases without bound of the ij entry of the matrix A sub k equals the ij entry of the matrix L. This would be true for every row I and column j for our matrices. Now this here is a sequence of mn limits for our sequence of complex numbers. So the point is that the very first statement says something about each and every extended real number, p, and we can talk about the p norms. For the second, this only holds for some extended number p0, and we could talk about the p0 norm. For the third, we don't even need to introduce p norms, we can just look at sequences of complex numbers. But again, the statement of the proposition is now all three of these are equivalent. It does not matter which of the definitions you choose. At the end, we make a following definition. If any of these equivalent statements are true, then we'll say the limit as k increases without bound of a sub k equals L. And we'll just say colloquially, the sequence converges to a limit L. Let's end today by going over the proof of this proposition. We'll break this up into three parts. First, we'll show that statement 1 implies statement 2. Then we'll show statement 2 implies statement 3. And finally, we'll show that statement 3 implies statement 1. Let's start with the first. Say that a positive epsilon is given. Since we're assuming statement 1, we know that for each extended real number p, we can find a positive delta such that the p norm of ak minus L is less than epsilon whenever k is greater than delta. Then clearly, for some extended real number p0, we can find a positive real number delta such that the p0 norm of ak minus L is less than epsilon whenever k is greater than delta. Again, if it's true for every extended number p, then it must be true for some extended real number p0. So this means the first statement does indeed imply the second. Next, let's show that the second implies the third. Again, say that a positive epsilon is given. We're going to assume that for some positive extended number p0, we can find a positive delta such that the p0 norm, ak minus L, is less than epsilon whenever k is greater than delta. In particular, let's take a look at the ij entry of our matrix. Well, we can take a look at the standard basis vector E sub j as a column vector times our matrix AK minus L. Now, looking at the way that we've defined the properties of everything, then we can see that the ij entries, aj, ij, minus l, ij, should be less than epsilon as well. But now this is true for every row I, column j, so in particular we've proven this now for mn limits of our matrices. Now, let's prove finally that the third statement implies the first. So we'll assume that we have mn limits. That is, for the ij entries, the limit as k increases without bound of ak, ij, should be equal to l, ij. Let's say that p is any extended number, and let's let q be the complementary modulus. That is, 1 over p plus 1 over q is equal to 1. Now let's say that a positive epsilon is given. Since we have these statements about these mn limits, we know that for each row I, column j, we can find a delta ij, positive, such that the absolute value of ak, ij, minus l ij should be less than this funny looking symbol here on the screen. This is epsilon divided by twice the pth root of m times the qth root of n, whenever, of course, k is large enough. Now, let's let k be larger than each of these delta ij's. Well, whenever p does not equal infinity, we see now that the p norm of the vector ak minus l times the column basis vector e sub j should be less than or equal to epsilon divided by twice the qth root of n. When p does equal to infinity, we actually find the same thing. So now we've shown that we can actually have the pth norm in all cases of the matrix ak minus l times the vector ej to be less than or equal to epsilon divided by twice the qth root of n. Now let's take a look at the following ratio. Here, for any vector x, we'll take a look at the product ak minus l times x, and we'd like to look at the pth norm of that. Well, playing around a little bit, we then find that the pth norm of ak minus l times x divided by the pth norm of x is less than or equal to epsilon over 2. However, recall the way the pth norm of a matrix is defined. It should be the largest of all such ratios. But we've just proven out that each of these ratios is less than epsilon over 2. So this means that the pth norm of our matrix should also be less than epsilon over 2, which of course is less than epsilon. But this is exactly what it means to say that the ak minus l has pth norm less than epsilon. So this completes the proof. As an example, let's consider the following sequence of matrices. Here, each AK is a 2 by 2 matrix where along the diagonal we have a lambda 1 to the k and a lambda 2 to the k. Using the previous proposition, we can actually compute the limit of the sequence by simply looking at the different cases, looking at lambda 1 and lambda 2. Let's take a look at when either lambda 1 in absolute value is less than 1, or each of our lambdas is equal to 1. If the absolute values of both lambda 1 and lambda 2 are less than 1, we've just proven that the limits for the lambda 1 to the k should be 0. So our matrix in this case has limit 0. Next, if lambda 1 equals 1 while the absolute value of lambda 2 is less than 1, our limit will be the matrix 1, 0, 0, 1. Similarly, if the absolute value of lambda 1 is less than 1 while lambda 2 is equal to 1, we find the limit 0, 0, 0, 1. And finally, in the case where lambda 1 and lambda 2 are both equal to 1, we actually find that the limit is the matrix 1, 0, 0, 1. Here the idea is that we're just computing the limits component-wise. We have 4 limits to compute because our 2 by 2 matrix has 4 entries. In particular, notice that the limit L is not invertible if either the absolute value of lambda 1 is less than 1 or the absolute value of lambda 2 is less than 1. We'll state one last result today, and we'll state it without proof. Again, say that we have a sequence of m by n matrices where the complex entries and we converge to some limit L. First, let's say that C is any complex scalar. Then the sequence corresponding to C times a sub k tends to the limit C times L. Second, let's say that P is some matrix, and let's multiply P on the left of AK to find the matrix P times a sub k. Then the limit of this new sequence tends to P times L. Similarly, let's say that Q is a matrix, and we can multiply on the right. Now we have a sequence AK times Q. Its limit tends to L times Q. Finally, let's say that each of our matrices perhaps is the power of some matrix. That is, a sub k is just a raised to the k. And let's let Q be any invertible matrix. Then if we take a look at the sequence defined by Q inverse, a raised to the k times Q, then this tends to the limit Q inverse LQ. This last statement we're going to use quite a bit in the next lesson. But for now, thanks for watching.